Hello there, guys. We are going to go through your feedback today for the second test you did, to the end of topic test for radioactivity. Now, this test here is heavily dependent on explanation work, so we need to make sure that we understand what's going on in terms of radioactivity, so to ensure that we are getting those marks. Okay, especially we need to look at the question itself to know exactly how many marks it's worth and how many stuff we need to write on. Okay, now any question you got no marks. Any question you got less marking, I need to see that you've done your proper pen properly. Okay, let's get started. Now the first one is we have beta particles. Now beta particles, we need to understand what is a beta particles. Okay, and how a nucleus changes. So how does the nucleus change when the beta particle is given off? Now first of all, beta particles is a fast moving electrons. Okay, so fast moving electrons. Now the beta particles, the fast moving electrons, which is emitted from the nucleus. Okay, so this is from the nucleus, because normally when we talk about isotopes, they are just it's mainly the nucleus. Okay, and then it normally take from that. We did look at it before when we did some papers. So nucleus, so it's fast moving electrons, emitted from them. So fast moving from the nucleus. So this will give you 1 mark. Now the second mark we get to when we talk about what else happening. So we know that one neutron changes or turns into one proton. Okay, so this is what happened inside the nucleus. So we got one proton that changed itself into, so we got one neutron that changes itself into a proton, and then we have one electron being emitted from the nucleus as well. Okay, so 2 marks, we need to say this. Alright. Now, there are also other possibilities. I'll just show you the mark scheme as well. Other possibilities we have is the neutron number decreases by 1. That's true, because we are changing. So we are, well, not technically, we're technically losing 1 neutron, but it's not going anywhere. It's just turning itself into a proton. So the neutrons goes down and the proton goes up by 1. Okay, but you get 2 marks for saying neutron changes into a proton and electrons is emitted. Okay, for 2 marks. Okay, just like we talk about. Okay, now let's talk about the Rutherford experiment. So Rutherford is so this experiment here is about Rutherford, and it's about the atom. Okay, the atom, and the main thing we are focusing on the atom is the structure of it. Okay, the structure of it. Now, Rutherford came up, so we need to explain the results. So in order to talk about the results, we need to talk about the observations. Okay, so 2 observations that he saw. So observations. Okay, and then I'll say results here, or conclusion. Let me just, the conclusion is much better. Conclusions. Okay, so 3 marks. Now ideally, I would like this to be 4 marks. Okay, I would like this to be 4 marks because we have 2 observations and 2 conclusions. But unfortunately, it's 3 marks here. So we need to be careful how we get that. So we need to mention all 4 points to get 3 marks. Okay, so first of all, we have some alpha particles. Okay, it goes straight through. Now it goes straight through the gold leaf. So we have the gold leaf here. So if I draw it to get up, so if I draw it up, so this here is a gold leaf. So let me just draw it here. Gold leaf. Now alpha particles. So some of them pass through. Okay. So gold leaf. So this is the gold foil. Most alpha particles pass through. Okay, that's the first observation. Now second observation, where you saw some alpha particles. Okay, are scattered. Okay, so scattered by large angles or bounced off. I just said the word scattered. Okay, so let's take a look. Some of them come here, get scattered. Okay, let me just carry this on. Let's bit down. There we go. And another one go through, get scattered. Okay, so these are scattered. Okay, now what did this mean? And we need to get the last mark. So what did this mean? So this means that, so here, this one here shows that atom is mainly empty space. Okay, so empty mean is empty space. The second one means that there is a tiny concentrated positive center, which is the nucleus. Okay, that's what Rutherford came. That's what that's the conclusion he came up with. Okay, so this way, so the atom is, you got the center which is positive. Let me just draw this a little bit big. So center of the atom is positive, and then we have empty space. So it means the electrons are around it. So empty space. Okay, so here this is empty space. Okay, so we've got 1 electron here. Okay, the first shell or something. As you can see, between the first electrons and the nucleus, there's empty space, and the nucleus itself is a tiny point, and it's positive. Okay, that is the reversion. This is the idea that changed the history of the atom very much. So it went from the plum pudding to this based on the observation and the conclusions. Okay, so we need to see this. Alright, now we have isotopes. So this question should be easy, because all you need to say is isotopes, because they have same number of proton. Okay, so there's 1 proton here, 1 proton here, 1 proton here, so there's the protons, but different number of neutron. So this one here has 0 neutron, 0 neutron, 1 neutron, 2 neutron. Okay, that's what we need to say to get the marks. Okay, so you can say same proton number or same atomic number or something like that. Okay, alright, so there are a few possibilities here. I'll just also show you the mark scheme. So same atomic number, same number of proton, same element. Okay, I may give those said same element a mark. Okay, same, so but for different number of neutrons, different mass number. Alright, okay, now this one here is the easiest one. So 9943 on the top. This is straightforward. Okay, right, now let's take a look at this one here. Now, this one here is talking about why do we need high temperature for this to happen. Okay. Now, high temperature, what does high temperature mean? So high temperature means, okay, high temperature means high kinetic energy. Okay, so they can move very fast to overcome so high energy. To do what? So to overcome the electrostatic force of repulsion. Okay, now why repulsion? Because hydrogen are positively charged. Okay, so hydrogens are pretty much a proton. Okay, there's only one proton in it. So pretty much this is what. So we need high kinetic energy so they can move very fast. Okay, so high kinetic energy so they can move very fast to overcome the electrostatic force of repulsion. Now, if you don't remember the word electrostatic, you can say to overcome the force of repulsion, because hydrogen are, they have the same charge or they are positively charged. Okay, in this particular case. Okay, positively charged. nuclei or nucleus. Okay, so 3 marks, 3 things: high energy, that's what temperature said, to overcome the repulsion, and because they are the same charge. Okay, now this one here should be straightforward. Okay, so E is equal to mc squared, E is equal to mc squared. We need to find mass, so rearrange it for mass. E over c squared. Now energy we know, so 4.5. Okay, divided by speed of light we know. Okay, now the squared here, so therefore we need to square this, and we get around 5 times 10 to the power minus 9, 29. Okay, so here we go. So here I've done it to 1 decimal. I've done it to 1 significant figures. Okay, so 1 significant figures. Okay, so if you want to leave in decimals, if you've got decimals, that's fine. 3 marks. Okay, this is the easiest question that you're going to get. One of the easiest questions you're going to get. Okay, here the equation, plug the numbers in and get the equation. Okay, so anyone who messed this up, you need to fix yourself. Okay, because this one here is easy, but quick. So quick and easy. Because all you need to know is just plug in and use the calculator. Okay, same thing with this one here. Plug in, use the calculator. Well, this one you don't need the calculator. You just addition and subtraction. Again, this here should be easy question as well. Okay, and the first one here also should be the easy question to get the marks. Alright, now we have the Geiger counter. Now we need to understand here that we have 2 rocks. We have 2 different rocks. Okay, and we want to get results for each of these rocks and compare it. Okay, that's what we need to say in this particular case. Okay, now let's take a look how can we do this. Okay, now let me take a look how we can do this. Okay, now first of all we need to place, okay, so it's 4 marks, so we need 4 points. Okay, so what we need to do is, if we have, let's say, this is a diagram. If I put the rocks here, both of them, okay, then I'll be getting, no, that's wrong. So I'll be getting both of them. I'll be getting both of them in this particular case. Okay, I'll be getting both of them here. Okay, so this reading here, I'll be getting both of them. So for example, I can get, let's say this is 50 and this is 50. Okay, no, let's say this is 50, this is 25. But what I'm reading on my screen, I'll be getting 75, and I have no idea which one is which. Okay, because I don't see 50 and 25. All I see is everything together. Now, what I want to know is, I want to know how much is this rock, so rock 1, how much is rock 2. Okay, now remember, this number here will be higher. Let's say, for example, it's going to be 175 because of the background as well. So background somewhere here. Okay, background. Radiation. So wherever you go, there's always background, so radiation being thrown out as well. Okay, so background as well. Okay, so the question is, how can we get the number from each rock? How can we get the count rate from each rock? So first of all, what I'm going to do is, we are going to measure the count rate for the rocks. How? I'm going to measure it separately. So what I'm going to do is, I'm going to measure the first rock first. So this way it will eliminate the reading from the second rock. Okay, so this way I have something like this. So this number here will go down. I'm going to have the first rock and the background as well. Okay, with this here, it makes it easier. Okay, so measure separately. So i.e. rock 1 first. Okay, that's what I'm going to do. Measure the rock first. Okay, now what I'm going to do is, I'm going to measure it for a measure for a. Okay. I can say I measure it for a certain amount of time, but I'm gonna go directly into the thing here. Okay. So we're gonna measure for rocks. Okay, and then I'll measure the background count by removing the rock. Okay, that's how I'm gonna get this. Okay, so we need to measure the background count by removing the rock. So this way, remove the rock. So if I go into my diagram again, so if I remove the rock, so what are we getting now? We're just getting the background. Okay, whatever the background is, we're just getting that. Okay, so we're taking into consideration the accounts. Okay, now what I can do is I can say, well, to make it more accurate, okay, I can repeat the above step a few number of times, okay, and then take an average, all right, and finally take away in this particular case. So what I'll do is so once we got the count rate, once we got background count, we can just say take the difference to get the count of rock 1. Okay. Number 4, sorry, I can just say, repeat above step, okay, to get an average. So this way we know exactly how much we're getting. And finally, what I'll do is I'll do repeat above steps for rock number 2. Okay, so this is the step to get the count rate from one reading for one rock, and all I'm doing is once I've done my fourth bullet point, so this point here, I just say repeat the above step for rock number 2, and hopefully we are going to get the same thing. So pretty much all we start with what we have. So we got a rock number 1. Okay, so rock number 1, when we read, so let's say this is 10, this is 10. Okay, let's say the background count is 10. Okay, so the background is 10. Let's say that this here is, I don't know, 50. Okay, so first of all, when I measure the count rate for one rock, so one rock number 1, so all I'm getting 60 here. Okay, however, I just want the 50. I have no idea it is 50. I only see 60. So therefore, what I need to do is I need to remove the rock. Okay, and what do I get? So this time on my reading, I get 10. 10 is from the background, so therefore I can easily do 60 take away 10. This gives me 50, and 50 is that of the rock 1. Now I'll do this a number of times and get an average. This way I know it is indeed 50 or not. Okay, that's the first one. And I'm going to do the same thing for a rock number 2. Okay, let's say rock number 2 is 70. So therefore, what I'm getting 80 here, and I do the same thing. I remove the rock. Okay, rock number 2. So this is where I get 10, and all I need to do is 80 take away 10, and I get 70 from rock 2, and therefore I know before I had 50, and now I had 70. These are for the rocks. Okay, because the problem here is if I have rock 1 and rock 2, okay, then what I'll be getting is let's say this is 70, this is 50, so I'll be getting 120 here, okay, sorry, not 130 including background, and this number here 130, I have no idea, is it rock 1, is it rock 2, is the background. So I need to know how to eliminate one by one. So you need to think about it. So if you need to draw, you draw. Okay, it helps you understand what is truly going on in this question. Okay, if you see what's happening, then we can easily answer the question in bullet points, as you can see. Right, now let's move to this one here. This question is 6 mark. We're talking about the graphite core. Now let's look at the diagram. Where is the core? So the core is here. So this here is my moderator. Movable rod. So these are the rods that moves in and out. Here we go. So they're here on the diagram. Okay. and this will be my control rods. Okay, 6 mark. How do they maintain and control? Right, so let's talk about this. So I'll do it as a table, as you can see. So put moderator here and control rod. Okay, now the moderator, what does it do? Okay, so moderator, what does it do? So the moderator, it slows down the fast moving neutrons. Okay, so this is, if you remember fission, let me just do a quick recap for you. Now fission, we have one neutron. Okay, it's fired at unstable nuclei, a stable nucleus. Okay, and this here become more unstable, and then you split, and then it splits into two daughter nuclei. Okay, they're smaller. All right, we get 1, 2, 3. So we get about 3 neutrons, and we get energy, which we need. All right. Now, so this here we slow down the neutrons. So slows down. Why do we need to slow down the neutrons? So this way, when the neutrons slow down, it has more chance of hitting the unstable nuclei. Okay, that's what we want for it to be able to do. Okay, so slow down the fast moving neutrons. Okay, so this has more chances of hitting or being absorbed. Let me just say hitting. So hitting the unstable nucleus to start fission reaction. Okay, that's what we want to do. All right. This increases. Okay, so sorry for the handwriting here. I'm using the computer, of course. This increases the rate of fission. Okay, so again, we're talking about maintaining and control. So this is how you control it. If you want to make speed up, then we use this. Now, control rods, we have 2 things. So control rod, we can lower it, and we can raise it. Okay, now when we lower it, what does it do? So when we lower it, what does it do? It's going to absorb extra neutrons. So if I go back up, so here we're getting how many? 3 neutrons. And these 3 neutrons can go and collide with another unstable nucleus. Okay? So what happened is the control rods are going to absorb these neutrons. Okay, absorb extra neutrons. So less available to start fission reaction. Okay, fission reaction. Okay, this reduces the speed or the rate of fission. Okay, and on the other hand, if we raise it, what will happen when we raise it? No extra neutrons absorbed. Okay. Fission process. Fission reaction occur plus speed up rate. Okay, So this is pretty much what happened. That's pretty much what happened in this particular case. Alright. Okay. So speed up rate of chain reaction. Okay. As you can see, it's easily to get 3 marks or 5 marks by listing these things there. Okay, now pause the video if you need to do that. So this should give you your 6th mark in this particular case. Right, and the last question we are here, and this is now half-life is here. Now it says to me that this carbon atoms, this substance, this radioactive source, will take 5,700 years to halve. Okay, so this half-life means it will take this much years to halve itself. So let me start. So at this beginning we have 1 million. So it means after the first half-life, okay, it's gonna drop down to half. So this number here will drop down to half. This will be okay. Keep going. So after the second half-life, this will drop down to half again. Okay. After the third half-life, this will drop down to half. Now, how many half-lives does it take? It takes 1, 2, and 3 half-life. And how much is 1 half-life? Okay, so 1 half-life is equal to 100 years. So it takes 3 half-life. So therefore, it's going to be 5,700 multiplied by 3. And how much will I get if I do this on calculator? I will get about 1. This is the answer. Now, this question here, for those of you who got it wrong, I need to see the working out. So this is how we do it. Make sure we do this properly. Okay, for those of you who got question 6 wrong, I need to see all the bullet points. Okay, there's 1, 2, 3, 4, 5, 6, 7 bullet points. Okay, for those of you who got question this one wrong or less mark, there's 1, 2, 3, 4, 5 bullet points. Okay, this one again, for those of you who get this wrong, I need to see the full working out. Same thing here again, 3 marks, 3 bullet points. Okay, if you miss 1 or 2, I need to see all bullet points in. Okay, same thing for this one. Okay, same thing for this one, all the bullet points. If you miss any marks, same thing for this one. Okay,